Hello everyone, I hope the Chapter 3 reviews are going well for you and watching the solutions video. As always, what I keep saying is please let me know if you have any questions. All right, so today we are going to start Chapter 4. What's a little bit nicer about this section is anytime we actually get into applications, most of the problems are going to have easier derivatives to look at. So I know at the end of Chapter 3 we had all of the derivatives of the trig inverses, all the rules for the logs and exponential functions, the derivatives of all of those. So I don't want to say push it aside, but kind of set it aside for right now. Like I said, when we come back after Christmas break, we'll definitely go back over some things, and then the test will be on the 6th. All right, so if you didn't get a chance yet to look at the Inspire Doc 4.1, please make sure you do that. It's also part of today's assignment too. It just goes over some terminology. There's some problems. It walks you through some pages of section 4.1 from the textbook to make sure you definitely look at those, read those over, and then at the very end, try the quick review at the beginning of this section. So chapter 4, obviously applications of derivatives. 4.1, we're going to start to look at extreme values of functions and how to find what are called critical numbers. All right, so our goal is to look for these critical numbers. It could just be one, it could be a couple, but we're going to call C a critical number. So C is a critical number if f prime at C is equal to 0 or f prime of C is undefined. So these are very important questions we're going to ask ourselves. So pretty much we find the derivative of our function. We set the derivative equal to 0. We see if there's any values, really for x, where that derivative would equal 0. Or we see what could possibly make the derivative undefined. So those are the two questions we're going to ask ourselves. Once we get these special x values that we call C, we have what's called critical points. So a critical point is just of the form, whatever that special x value is, we'll call it C, and then f of C. So we just find that point in our function where our derivative is either equal to 0 or it's undefined. All right, so go ahead and pause this page and just make a quick sketch of each graph here. So sometimes we're going to be given a function, other times we're going to be given a graph, and we just want to know how many critical points. So in other words, we're going to answer the two questions here. And again, pause the video at any point you need to still copy the information down. The two questions we're going to ask ourselves are the derivatives here, but graphically we know that our derivative is the same as the slope of our tangent line. So here we're going to ask ourselves two questions. Where's the slope of our tangent line, which is equal to f prime of x? Is it ever equal to 0? Or is the slope of our tangent line, which is equal to f prime of x, ever undefined? So if we take a look at the first graph, anytime we have a slope of a tangent line that's 0, that means we have a horizontal tangent line. So looking at this first graph over here, are there any places we could fill in right in horizontal tangent lines? Hopefully you're thinking right up here, we would have a horizontal tangent line. Because going up alongside, we would have positive slopes here, and then it flattens out to turn, and then likewise down here. Now, it's no coincidence that notice this happens at a peak and a valley, and then what we're eventually going to call maxes and mins. Let's make this look more horizontal, though. So over here, we would say we have two critical points. We would have one critical point up here and another critical point down here. So again, this is where the derivative is equal to 0. So I'll just kind of draw two notices here. So in this case, f prime of x would equal 0. Nowhere on this blue graph would we have a vertical line. We would never have a vertical tangent. There's no place here to draw on a vertical tangent. But over here for the second graph, The ends here are really going towards horizontal asymptotes, so they're not actually horizontal themselves. But what we could have is right here in the middle, perhaps a vertical tangent line, like right here. And it's okay if it goes through because I'm just extending it so it's a little bit easier to see. So in this case, we would have our derivative would be undefined. The slope of the tangent line is undefined. So here we would just have one critical point. So f prime of x is undefined, or the slope of the tangent is undefined. Likewise over here, f prime of x is equal to 0, or the slope of our tangent is equal to 0. All right, so when you guys were in algebra, probably a little bit in algebra 1, but more so in algebra 2, we were analyzing graphs, and all we could do is go to the Analyze Graph feature on our calculator on a graphs page, and we would actually just kind of either do graph trace or do the Analyze Graph feature and find the max and the min. But now we can use calculus to help us out with these ideas here. So if we could find the critical points and then answer these two questions, so that's going to be our goal. And this is a way to verify that we have a max at this certain point or x value and we have a min at another x value. So let's go ahead and practice this. All we have to do right now, we're going to eventually put this all together, and down the road we'll be able to fully analyze all aspects of a graph. But for right now, the focus is just to slowly or gradually get into section or chapter 4. So right now we only want to find the critical numbers for this function f of x. So what you first want to do is go ahead and find f prime of x. Like I said, much easier than all of the derivative formulas we had to use and derivatives we had to find in the previous chapter. So this just should give us 3x squared minus 12x plus 9. But don't take this for granted. Always still double check. If we leave out one little piece, have one incorrect sign, it's going to affect the rest of our problem. All right, so now what we want to ask ourselves two questions. Is f prime of x ever equal to 0? Is f prime of x ever undefined? So let's do this first one. We're going to just go ahead and set 3x squared minus 12x plus 9 equal to 0. Now always try to solve by factoring first. A lot of the times, especially the beginning problems we're going to work with, should factor somehow if it's quadratic. Then if you absolutely cannot factor it, then we go to the solve feature on our calculator. But here we could factor out a 3, and we're left with x squared minus 4x plus 3. We could factor this further into an x minus 3 and an x minus 1. Set each factor equal to 0. The 3 first, if we set that equal to 0, that doesn't make any sense, or we can divide both sides by 3. So this x minus 3 will give us a value of x is equal to 3 or x is equal to 1. Now over here, is f prime of x ever undefined? Well, this is a polynomial function. More specifically, it's a quadratic function. It's a parabola. So a parabola is never undefined. The domain here is all real numbers. So we're just going to put f prime of x is never undefined. So our critical numbers, not asking for the critical points, just the critical numbers. We'll say, therefore, the critical numbers I'm fine if you want to make the little number symbol here, hashtag. The critical numbers are x equals, I know I called it c before, but the c is just the specific value. We just say x equals 1, 3. Now, if I asked you for the critical points, we would take the 1 and the 3 and substitute it back into here. But I'm not asking for that just yet. We will eventually do a problem where we figure that out. So the very start of all of these problems is to find the first derivative. Ask yourself two questions here. Is f prime of x ever equal to 0, or is it ever undefined? Any x values we get fall under the definition of them being a critical number. All right, let's try this with another example, but of course this involves trig. Here we just want to find the critical numbers in the closed interval from -pi/2 to 3pi/2 of y is equal to sine x. First, what I want you guys to do, we're just going to do this graphically, kind of how the first two examples we were just looking at graphs. So just go ahead and graph y equals sine x. just over the interval from negative pi over 2 to 3 pi over 2. Okay, so pause the video if you need more time. All right, so again, if you remember, the graph of sine definitely goes through the origin here. Pi over 2, sine of pi over 2 is 1, back down to 0, and then at negative 1, and then even over here, we're at negative 1. So it starts to look like this. All right, so again, we're just trying to draw in tangent lines that would either be 0, so horizontal tangent lines, or any vertical tangent lines. Now, if you notice here, this should be clear to see that we have a max right there, so we would have a horizontal tangent line. Now, even though they're at the endpoints, we would say right here, we would have another horizontal tangent line, and even right here would be another horizontal tangent line. Let's kind of draw that in a little bit better of what the graph is going to look at. So whenever we're on a closed interval, this could happen as well. So just looking at this, we would say our critical numbers are, we could even abbreviate, we would have x equals, we've got the negative pi over 2, pi over 2, and then 3 pi over 2. Let's verify this algebraically, or if I ever use the phrase analytically, that means algebraically. So by using calculus here. So in this case, let's first go ahead and find the derivative. So y prime is going to equal what? The derivative of sine x is cosine x. So we're going to ask ourselves the two questions here. Is y prime ever equal to 0? Is y prime ever undefined? So think of the graph of cosine x. Is there ever a value where the graph is undefined? No. So we'll say never undefined. However, cosine x is equal to 0. Keep in mind, we're just going from negative pi over 2 to 3 pi over 2. So if we start at negative pi over 2, that is 3 pi over 2. So we're starting down like right here on the unit circle. And then we're just going around this way. So this is negative pi over 2 all the way back around to 3 pi over 2. So cosine is 0 right down here at negative pi over 2. Cosine is 0 also up here at pi over 2. And then back down here at 3 pi over 2. So that verifies what we were finding up here. So these are the critical numbers. All right, so in the Inspire doc, you looked at some terminology for types of extrema. So let's take a look at these. All right, one type that was mentioned was absolute or global. So out of the entire universe here, the entire world, if we want to narrow it down some, absolutely the highest value on the graph, the y value, of course, or absolutely the lowest value. So absolute extrema means there are no other points higher than this absolute max, or there's no other points lower than this absolute min. So it's global. But relative extrema is just in the neighborhood. We're local. So if we kind of zoomed in on something, it's the highest relative to everything around it, or it's the lowest y value relative to everything around it. All right, so if we take a look at the first graph, again, pause the video if you need more time to copy this down. Now, absolute is going to be a guarantee, and I want you guys to read back over that extreme value theorem. We will be talking about that when we come back from break. An extreme value theorem happens on a closed interval, and it's a guarantee that we're going to have an absolute max and an absolute min. So if you look at this blue graph, we are on a closed interval. This graph does not go on forever. Out of all of these y values, right here would be the absolute max. Now again, the absolute max is the y value. So all of our phrases, when we go to answer these, we're going to say the absolute max is y equals this when x equals that. So an absolute max, you're going to see it answered as an ordered pair, but we never want to write it. It is technically not correct as an ordered pair. We want to say the absolute max is the y value. It occurs at this x value. Now based on this nature right here, we would say right about here would be the absolute min. So this graph, I'm just trying to point out absolute maxes, absolute mins. So this is a guaranteed when we are on a closed interval, in this case. It also happens with polynomials of even degrees. Even if we're not on a closed interval, if we think of y equals x squared, we have a parabola that opens up, so we're definitely going to have an absolute min. If we look at y equals x to the fourth, or any degree of 4, we're going to have an absolute min if it opens up. We can have an absolute max if it opens down. So I'll also write this out as polynomials of an even degree. Is it possible to have a combination of absolute extrema and relative extrema? Absolutely. But I'm just looking at them separately here. All right, so in the second graph, what we would call this max would be a local or relative max. I just like to abbreviate this way. Because obviously over here, there's points that are higher, but we are just kind of in this neighborhood right now. And then over here, we would have a relative min, because we're just in this neighborhood here. Obviously, this graph keeps going down forever, but we're not over there. We're just looking in this neighborhood that's over here, so just local. Okay, so we're going to practice a problem that sort of is connected to, it's an example of using the extreme value theorem, but I haven't officially introduced that yet. But here we are going to find the absolute or global extrema for the function g of x is equal to the cube root of x on the interval from -1 to 1. So what I first want you guys to find, let's go ahead and rewrite g of x as equals x to the 1/3. So again, pause the video if you still need time to copy that down. All right, so what I want you guys to do carefully now is to find g prime of x. That's our very first step. Do this carefully. Watch your exponents. So if we're just using the power rule, so this is going to become 1/3 and then x, and if we do 1/3 minus 1, 1/3 minus 3/3 is going to give us a -2/3. So let's definitely rewrite this because we have to ask ourselves the two questions. So we want to work with the best way to write this if possible. So we're going to write this as 1/3 times x to the 2/3, but let's write this as a √2 just in case this helps. So this would be the cubed root of x squared. So hopefully that makes sense. So now we have two questions to ask ourselves. First, is g prime of x ever equal to 0? Next, is g prime of x ever undefined? So we have a fraction here. So if we were to set 1/3 times the cube root of x squared equal to 0, I could think of this as two fractions if I put 0 over 1. Or if I just multiply both sides by the denominator, I pretty much would get a 1 is equal to 0, which is a false statement. So this is never. Or if you ever want to look, if we have a fraction, the only way a fraction can ever equal 0 is if the numerator is going to equal 0. The numerator is 1. There's no variable there, so it can never equal 0. But now over here, if we try to figure out what would make this denominator equal to 0, so this is undefined when the denominator is equal to 0. So we just set 3 times the cube root of x squared equal to 0, which just means the cube root of x squared is going to equal 0 if I divide both sides by 3. So the only way we're going to get a 0 here is if x is equal to 0. So we only have one critical number. Is x equals 0. However, because we have a closed interval, let me go back to this picture. Notice at the endpoint, that's also where an extreme value, an absolute max or min can occur. So not only do we have to check the critical numbers, we also have to check the x values of either end of the interval. So in this case, whenever we're asked to find absolute extrema over a closed interval, we're going to make a table. So this table, we're going to have our x values, and we're going to have, in this case, g of x. So we're going to include, we were going from -1 to 1. I want to have -1. I also want to have the 0. So we include the x values that are the ends of the interval as well as any critical numbers in between. So now if we say g of x was equal to the cubed root of -1, which will give us -1. Let's write this in here as g of -1. Next we'll have g of 0 is equal to the cube root of 0, which is 0. Then we'll have g of 1 is equal to the cube root of 1, which is 1. So this is how we're going to phrase this. So clearly this is the lowest number out of the 3. This is the greatest. So we're going to say that the absolute max, this is how we always want to answer this, the absolute max is, say, y equals, or g of x equals 1, our largest number, when x equals 1. Or you could just say the absolute max is 1, but to kind of point out for sure that that's the y value. Then we want to say the absolute min is y equals -1 when x equals -1. So these are our two answers. Let's go ahead and graph this by hand. So if you think of the graph of y equals x cubed, the graph of y equals the cube root of x is just going to be the inverse, and we're just going from -1 to 1. And we can just plot these 3 points if you want. And then we want to carefully just draw a curve going through it. But remember, it's going to be the inverse of the graph of y equals x cubed. So pause the video to go ahead and sketch that, and then I'll scroll down to show you what it should look like, or the close resemblance of it. All right, so let's go ahead and take a look. So it starts to look like this, kind of curves a little bit. Didn't really draw that, showing it too well here. It will look like this. So if you notice, out of this value, even though 0 does show up, it's actually, when we get to it, it's actually called something else. The point at 0 is not a max or a min, but it's something else related to the behavior of a graph. But right here, we have a max, absolute max at y equals 1 when x is 1, and then we have an absolute min over here. So let's write this in. This is the absolute max, is the y equals 1 when x is equal to 1. Down here we have the absolute min, is y equals -1 when x is equal to -1. So this is how we could use the derivatives to help us find extreme values. All right, so please continue working on your test corrections. Make sure you email me or join a Zoom meeting. Any time of the day really is fine. Just let me know if you have any questions over the test corrections. Please continue on the Inspire Doc 4.1, the quick review assignment. And then I want you to try GIF 4.1, 1 through 6 all, then 7 through 25 odd. And I just want to go over something with you. So I'll definitely, like before, I'll have a separate PDF. All right, so for 1 through 6, notice the directions. It says find the value of the derivative if it exists at each indicated extremum. Also state what type of extremum. So state whether it's an absolute max or an absolute min. So these are all just over, we'll call them closed intervals. Notice there's no arrows on the ends here. So notice that number 1, I'm just going to kind of work this one out for you just so you know how to state the answer. So I'm not asking for you to state it like we did in our last example. In this case, we have, if you notice the point that's right here. So we would say we would have an absolute min that's going to occur at the point 0, 0. So for right now, it's okay to say the absolute min. I'm not asking you to find it, I'm just asking you to state what type. Then you can also say at 0, 0, the derivative is equal to 0. We would have a horizontal tangent line here. So it's either going to be the derivative is undefined or the derivative is equal to 0. So you're going to do that for 1 through 6. They've already indicated the point that the max or min will occur. So you just have to state, do we have an absolute min at this point? Do we have an absolute max at this point? The derivative is 0 at this point, or the derivative does not exist or is undefined at this point. Then when you look at 7 through 25 odd, this is like the last example we did. or the last two. So for 7, 9, and 11, you're only finding the critical numbers. And for 13 to 25, determine the absolute extrema of the function and the x value in the closed interval where it occurs. So this is where you want to state your answers as a sentence here. So you would want to say the absolute max is y equals this when x equals that. So notice they give you the closed intervals for all of these. So this is where you want to find the derivative, ask yourself 2 questions, create that table, and then answer in that statement for the absolute max and absolute min. All right, so I will post this as a separate PDF. As always, guys, take care. Let me know if you have any questions.